Hello everyone and welcome back to Intelligent Machines. In the last video, we saw how a diffusion model can generate structured data like images starting from pure random noise, something like this. We understood how a seemingly random data distribution gradually transforms into meaningful structure when trained step by step to denoise. That was the foundation of diffusion model, and it truly changed the game in generative AI. We also looked at how the model takes a timestamp as input, the noisy input, and learns to predict how much noise has been added or how much noise can be removed at each step using the unit architecture. Before we start today's topic, let us first look at one major limitation of what we saw earlier. Previously, our model could generate random samples after training. Could be any thing from this, but we had no control over what thing to generate. Imagine we have four classes, let's say cat, dog, elephant, and platypus. If we project all their images into a 2D space, we'll see four different classes, 1, 2, 3, 4. Now after training, when we start generating from random noise, the model can produce any of these class. It can be a dog, a cat, or anything with pretty much equal probability, given they have same amount of data during training. We cannot control the class of image that has been generated. This is what we call unconditional image generation. And this lack of control is the problem. In practice, we need conditional generation where we can tell the model what we want to generate. So how do we gain control? By introducing class label as an additional conditioning input. Before, we only provided the noisy image and the timestamp to the unit. Now we will add one more input, the class label. During training, we take an image from, let's say, cat class, one image from cat class. We pass it to the unit. Of course, we add some noise and we pass it to the unit model along the corresponding class label, let's say class label 1. The model then learns to denoise this image with respect to the class label. Later during the generation, when let's say our unit model is fully trained and we are starting from random noise, we can feed this label again to the unit during the generation process. For example, let's say label 3, which correspond to platypus. Then the model will generate an image which correspond to the platypus. This small addition gives us control over what the diffusion model generates. And this exact class label in the future turns out to be the text conditioning. Now, when we give it a text prompt and generate something, this is the basic idea of that we condition it on something. Once we fine tune the unit model using the conditioning of label, we can generate a given class as long as that has been used for the training of the unit. The code for this video is available in the description and also on my GitHub. It is the same notebook we used earlier, now just extended for conditional diffusion model. So we can create our dataset using this datasets.makeblobs method. We are having four different clusters, and then we are normalizing our dataset using mean and standard deviation so that the dataset has a mean of 0 and standard deviation of 1. One additional thing is now along with the dataset, we have corresponding labels as well. If we plot them, you will see there are four different groups each belonging to the different labels. Our goal is to add noise to these data points and then train a model to denoise them back to their original structure. But this time, conditioned on their labels. We already discussed about the scheduler in depth in the previous video, how it controls the amount of noise added at each step. In the forward diffusion, we start with the clean data. Here x0 is the clean data. We sample random noise and add that noise to the clean data to get the noisy data. xt1 is the noisy data, which we plot here. If we visualize it, we can see that how the original cluster disappears into what it looks like pure noise. I even marked one point in black to track how it moves during the process. After enough steps, everything looks completely random, and this is exactly what we want. Now let us look at what changes inside the unit. Previously, our model took two inputs, the noisy data and the timestamp. The timestamp went through the embedding network and the generated timestamp embedding was added to the intermediate layers. Now we add one more conditioning input, that is the class label. The class label also goes through the embedding layer and we add the embedding together with the time embedding at different points in the network, different intermediate steps, and that is it. So there are only two small changes. One is this extra class embedding layer and addition of that class embedding layer throughout the intermediate steps. That's it. To give more information to the model about the class label. Then we create an instance of the model, the unit basically. And now this is the training phase. First, we define the loss function, the optimizer, and these are the scheduler parameter for the forward diffusion step. For each iteration, we sample random noise, we sample a random timestamp, we add the noise to the clean data according to the forward process, we feed the noisy data, timestamp, and class label into the model. The model predicts the noise. The model predicts the noise that was added. We compute the loss between the predicted noise and the true noise. Then we backpropagate and update the gradients. As the training progresses, you will see the loss gradually decrease, which happened in our case. So after training, we see that the loss drastically decreases, but after a while, it just stays same and keeps on oscillating. Now we'll see how we can generate new data. Once the model is completely trained, now we are able to generate new data samples. We begin with completely random noise and then iteratively denoise it, starting from the highest time step and moving back to zero. That's why it is reversed. At each step, we sample the required parameters from the scheduler, alpha, beta, alpha bar, and use the DDPM formula. These are the DDPM formula to compute the mean prediction. We also add a small random component as part of the stochastic process because this all are part of a stochastic differential equation or SDE. Now let's run this and we'll see. So we start with seemingly random distribution. This data starts with pure noise, but gradually it forms distinct clusters again. We can clearly see the transformation. For example, I'll run this again and focus on the black points at this point. We label the black point as blue and it should go to the blue cluster every time because here this one, because label 0 is blue, it belongs to the 0th class. So that's why the black dots during the starting, wherever it starts, it will end up in the blue cluster after the diffusion process. So that is the power of conditional diffusion. And this demonstrates that our model is now conditionally generating data based on the label we provide. Initially, the denoising process is modeled as stochastic differential equation. Stochastic means nothing but we add some noise during the denoising. We add some noise. There is some randomness involved in this process. But eventually, researcher proposed that we can do it using ordinary differential equation as well, where we don't have to add noise. If we follow that, we'll go more into this ordinary differential equation formula. The difference is just here, this part. Rest all stays the same. And if we run this, you'll see the generation is now the generation is way smoother and allows for us to do this in very few denoising steps. We'll explore more in this topic in the upcoming videos. So to summarize, today we'll learn how to turn our unconditional diffusion model into a conditional one by adding class label as an extra conditioning input. In the next video, we'll move from simple 2D points to real images, starting with the classic MNIST dataset, which is basically the hello world of computer vision. We'll see how to generate handwritten digits like 1, 2, all using diffusion model. And we'll do this in two ways. First, by building our own diffusion pipeline, and next by using the diffuser pipeline, the Hugging Face diffusers library. These are all generated images. Thank you for watching, and if you are enjoying this series, do not forget to subscribe. I'll see you in the next video.